Before a mammal takes its first breath, it develops in a highly regulated, pristine environment, isolated from the physiological chaos of the outside world. Yet, clinical data reveals a strict correlation. Individuals born with abnormally low birth weights carry a statistically higher risk of developing severe chronic illnesses decades later in adulthood. By their 50th year, these specific populations show disproportionate rates of hypertension, type 2 diabetes, and severe psychiatric anxiety. This presents a biological paradox. It defies logic that a transient 9-month gestation period can permanently dictate a physiological collapse half a century later. This animated data visualization plots the relationship between decreasing birth weights and adult disease. As the birth weight drops, the risk percentage for cardiometabolic disorders continuously scales upward. These are not random genetic errors. They are mathematical probabilities directly tied to maternal malnutrition and stress. Biologists classify this phenomenon as developmental programming. When maternal stress reaches a critical threshold, it breaches the placenta's chemical defenses, triggering a cascade that permanently rewires the developing fetus's neurochemistry. An adult's health does not begin as a blank slate at birth. It is strictly tethered to the precise chemical states endured inside the womb. To understand exactly how this damage occurs, we have to look past macroscopic epidemiology and examine the cellular interface of the fetal-placental unit. The fetus is not naturally immune to circulating maternal stress hormones. It relies entirely on a dedicated, highly specific biological defense system. This primary chemical barrier is a placental enzyme known as 11-beta-HSD2. This schematic demonstrates how the enzyme functions as a molecular filter. As active maternal glucocorticoids, like cortisol, approach the barrier, 11-beta-HSD2 intercepts and catalyzes them into an inactive state, cortisone, before they can enter the fetal bloodstream. But this system is fragile. Severe psychological stress, maternal malnutrition, or a lack of oxygen introduce hostile chemical signals that bombard the maternal side of the barrier. In response to these triggers, the placenta actively downregulates the production of the enzyme. The 11-beta-HSD2 defenders rapidly decrease in both number and efficiency across the membrane. With the enzymes depleted, the barrier completely fails. A toxic flood of uncatalyzed active glucocorticoids bypasses the membrane and pours directly into the fetal compartment. This influx is particularly damaging because it frequently coincides with late gestation, a critical window of rapid neural generation in the fetus. The idea that a fetus is chemically isolated is an illusion. A mother's severe physiological distress directly infiltrates the womb, chemically altering the structural architecture of the developing fetal brain. Once past the placenta, these active stress hormones enter the fetus's systemic circulation and travel straight to the brain. This technical diagram illustrates the hypothalamic pituitary adrenal, or HPA, axis. On the left side, we see the baseline flow where the hypothalamic, pituitary, and adrenal glands communicate to manage a healthy stress response. The system relies on a strict shutoff mechanism. Cortisol, produced by the adrenal gland, travels back up to the hippocampus, where it must bind to glucocorticoid receptors. This completes a negative feedback loop, suppressing the system and ending the stress response. When the fetal brain is flooded by excess maternal glucocorticoids, that baseline shifts to the pathological state mapped here on the right. Reacting to the massive overexposure, the fetal hippocampus aggressively downregulates its own production of glucocorticoid receptors to protect itself. Without a sufficient number of receptors, the hippocampus cannot detect the cortisol circulating in the blood. The negative feedback lines break, failing to inhibit the hypothalamus and pituitary. The result is a chronically hyperactive system. The brain constantly issues commands to release more hormones, causing a relentless, cascading overproduction of cortisol. Over decades, this chronic mild glucocorticoid excess exacts a heavy physical toll, wearing down the cardiovascular and metabolic systems, much like the pathology of Cushing's syndrome. By stripping the brain of its cortisol receptors in utero, the organism loses its biological brakes. it is guaranteed to operate in a severe state of high alert for the rest of its life. Why does a temporary reduction in fetal receptors become an irreversible trait in adulthood? The answer requires us to shrink our perspective from the systemic brain network down into the nucleus of a single hippocampal cell. The mechanism is epigenetic. This means the actual DNA code remains intact, but the physical structure dictating how that code is read undergoes a permanent alteration. This animated diagram isolates the exact location where this programming occurs, the exon 1-7 promoter region of the glucocorticoid receptor gene. When the maternal stress flood hits, it induces DNA hypermethylation and histone hypoacetylation. Methyl groups aggressively attach to the DNA strand directly at the promoter region, physically tightening and restricting the chromatin. Normally, a transcription factor known as NGFIA needs to dock at this specific promoter to turn the gene on and manufacture the necessary receptors. But the hypermethylation creates a condition called steric hindrance. The NGFIA protein is physically blocked by the clutter of methyl groups and fails to access the DNA sequence. Consequently, the gene remains permanently silenced. The receptors are simply never built. Maternal distress and early trauma leave a structural signature in the folding of the hippocampal DNA. This transition from a transient chemical state to a permanent architectural trait is written into the genome's physical structure. To understand the true scale of this structural signature, we must zoom out from the DNA strand and look at the chronological arc of an affected human life. This flowchart maps out the entire chain of causality we have uncovered, beginning at the top with a maternal environment compromised by stress or poor nutrition. This distress travels down, breaking the enzymatic barrier and severely decreasing the 11-beta HSD2 function within the placenta. As we follow the path into the fetal environment, the fetus reacts to the influx of hormones by executing a series of specific physiological adaptations, actively restricting its own growth and enhancing its metabolic efficiency. Biologists refer to this adaptation as the thrifty phenotype. These changes are not a biological malfunction, they are a predictive evolutionary feature. The fetus is optimizing its body to survive in a harsh environment characterized by extreme caloric scarcity and high predation. But a crisis emerges when we trace this timeline into adulthood, where the programmed phenotype collides with the reality of the postnatal environment. This highly efficient, stress-primed organism is suddenly thrown into a modern industrial society, a world with unlimited caloric density and zero natural predators. This severe biological mismatch between ancient fetal programming and modern reality is the exact mechanism driving our current epidemic rates of type 2 diabetes and hypertension. Modern cardiometabolic disease is a consequence of a survival mechanism performing a strategy designed for an environment that no longer exists. The body is successfully executing a prediction for a world that simply does not